In this video, we're going to see how to calculate expected values for a binomial sample using our Ti Nspire, and that's particularly useful for chi-squared goodness of fit tests, where you have to do a comparison between expected values and observed values. So before we get into the example, I want to just clarify the difference between expected value of a distribution and expected values of a sample. So the expected value of a distribution depends on the distribution. If you have a normal distribution, the expected value, what you expect to get from that distribution, is the parameter mu, that's the mean. If you have a Poisson distribution, the expected value is the parameter lambda, which is the mean and the variance. If you have a binomial distribution, the expected value is the product of the parameters n times p, where n is the number of items that are being checked or volunteers, and the probability of success is p. So, and success is whatever you define it to be as the researcher. That distribution would look like this, this bar chart right here. The expected values of a sample are frequencies. And so these are how many occurrences you might get in each of these bars. So this is a probability distribution here, but if you had a sample of, say, 100 volunteers and you want to know how many of them are successfully testing positive for, you know, being cleared of a virus or something like that, testing negative, but you want to know how many people fall into 0 of something, 1 of something, 2 of something, 3 of something. And so the expected values are actually frequencies. So you could write that the frequencies equal this. And so the formula here, regardless of what type of distribution you're using, is the sample size times the probability of a particular outcome. And so that is also written as n times p. So we don't want to confuse this with the n times p up here, because the n in a binomial distribution is different than the n in a sample size. That's a different n. And we'll see an example that hopefully clarifies that. If you want the frequencies or the expected value for outcome 1, you would take your sample size times the probability of outcome 1. If you want the frequencies or number of occurrences for outcome 2, you would take the sample size times the probability of outcome 2. And you would do this for however many outcomes you have. So if you only have a few different outcomes, you can easily calculate this by hand, or just in a calculator page on the Ti Nspire. But if you have a lot of outcomes, there's a way to do this in the TI's spreadsheet that makes it go a lot faster. So here's an example using a binomial distribution, and in another video, I'll do a Poisson distribution. A package containing 4 bulbs claims that it has an 80% success sprouting rate. You test this claim by purchasing 100 packages, planting them, and then recording how many bulbs out of 4 sprout from each pack. Let X be the number of sprouted bulbs in a pack. So the number, our null hypothesis is that the sample, here our sample is 100 packages, comes from a population that would be, you know, a factory that's producing all these bulbs, where you have a 4-pack where you could have 0 bulb sprout all the way up to all 4 bulbs sprout, and each bulb independently has a sprouting success rate of 80%. The alternate hypothesis is that our sample does not come from this population. And that either means that our packages came from a different factory, or maybe it means that our sample came, that the factory is not doing what it claims. It does not have an 80% success rate. And so here's an example where I just want to point out the sample size is 100, but the n for the binomial distribution is 4. So those are different values. From your sample, you observe the following frequencies for successfully sprouted bulbs. So these are sprouted bulbs. How many sprouted? Number sprouted. Only one package had no sprouting. Only two packages had a single bulb sprout. 16 packages had two bulbs sprout, and then 43 packages had three bulbs sprout, and 40 packages had all four bulbs sprout. So if you were to graph the frequency distribution, this is what you would get. If you were to convert this, however, into a probability distribution like this, would it be close enough to this null hypothesis, this claim, that you can accept the null hypothesis? So in order to do that, we have to actually we have to do a chi-squared goodness of fit test, and we have to compare the observed values that we have right here in the table to the expected values or the expected frequencies, and that's what we're going to use our Ti Nspire for. So what you're going to do is open up a new spreadsheet, and I'm going to enter my possible outcomes. So I could have no bulb sprouting from a package, one sprout, two sprout, three, four, all four sprouting from a package. And then what we want to do is get the probabilities. So you can type in prob, you can type in just letter P, you can type in PX. So here I want to get the probabilities so that in the third column, I can use the probabilities and my sample of 100 to calculate expected values. My observed values can go in another column, and what we observed was 1, 2, 16 packages, 43 packages, and 40 packages. So now let's get the probabilities for each of these outcomes. In this cell, the one that has an equal sign, we're going to type equals. And you see how it came up with the column title and then colon equals. That means we're defining it to be. And we're going to do a binomial PDF. Statistics and binomial PDF. So each package had 4 bulbs in it. Probability of success was 80%. Enter that as a decimal. The X value, we're going to arrow over and choose the title of column A. So those are the X values. We're going to pull every single one of those. And you can check down below and see what you've got. Just double check your work and then hit enter. And it will autofill right there. So you can see the probabilities are very low for 0 and 1 and moderately high for 3 and 4. So now let's go to the next column over here, equal sign, this row, and just clicking in it, that popped up. If it doesn't pop up for you, that you might have to actually hit the equal sign. Now we're defining this expected value column, and we're going to do n, sample size 100, times column B. So I'm going to type in prob, and you see how it turned bold? So when I typed in this column title, it knew I'm pulling from each of these cells. So I'm going to hit enter. And so 100 times this probability gives me that. 100 times this probability gives me that. That makes sense. Okay, so this is what I should expect to get. Notice that expected values, these frequencies, expected frequencies, are not necessarily whole numbers. You can't actually get 2.56 bulbs sprouting. You either get 2 bulbs or 3 bulbs, but not 2.56. These are expected values. And then for the chi-squared goodness of fit test, we're going to compare these expected values to the observed ones. So go into another empty cell, menu, statistics. I'm going to go down to stat tests, and we're going to choose a chi-squared GOF goodness of fit. My observed list I titled OB. The expected data I titled EX. So degrees of freedom is the number of outcomes that you could possibly have minus 1. So we had 0, 1, 2, 3, and 4 are all the different outcomes. There's 5 different outcomes for how many bulbs could sprout, minus 1. So we'll do 5 minus 1 is just 4. This is where we're going to pop out our results, hit enter. And there's the chi-squared test statistic. In IB, you don't really need this. I don't think they actually ask for this. If they are, then that's what you would write down. The p-value is right there. There's your degrees of freedom. And don't worry about the other things in the list. So we've got a p-value of 32%. If we were doing this hypothesis at a 5 or even at a 10% alpha, then our p-value of 32% is definitely higher than the alpha of 5 or 10%. So we would keep our null hypothesis. We can keep believing that our sample of packages comes from a binomial distribution with an 80% success rate. So just to sum it up, in your spreadsheet, you're going to type in all your X values, all your possible outcomes, then calculate the probabilities defining this column to be a binomial PDF, referencing the first column, outcomes, as your X values. To find the expected values, you take your sample size, multiply that by the probability column over here, and that'll do it. Now, this is such a small, this does not have very many outcomes, and so if you wanted to, you could do this on a calculator page. So I'll just show you quickly how to do this on a calculator page. You go Menu, Statistics, Distributions, and we would go Binomial PDF, Number of trials for probability of success is 80%, and we're just going to hit X. So just a variable. We're going to hit Enter, and there are all 5 different probabilities. If I then take that answer and I hit times by the sample size, Enter, then these are the 5 different expected frequencies that I should be getting. Now that's fine here, but you can see that if you had a whole bunch of different outcomes, then this list would get really long, and it's kind of hard to read it, and you'd have to arrow over, and it just gets tricky. So I do recommend that you do these expected values in a spreadsheet. The other advantage is that you can then just add in your observed values and then perform a chi-squared goodness of fit test all in the same spreadsheet. I hope that was helpful.